Welcome to The Explainer. We are diving into something today that is absolutely foundational to modern artificial intelligence, but honestly, it almost never gets the spotlight it deserves. We always hear about these massive AI models with trillions of parameters, right? But what we don't usually hear about is how they actually manage that colossal workload without completely burning out, or frankly, requiring a supercomputer the size of a city just to answer a simple prompt. Well, the secret sauce is a system called Mixture of Experts, or MOE for short. Today, we're going to explore exactly how AI acts as its own internal traffic cop, routing information intelligently to save time, save compute, and achieve just staggering scale.
Here's our roadmap for today. First, we'll go inside the MOE architecture, then we'll uncover the load balancing problem, explore 3 different routing solutions, and finally, wrap up by comparing some real-world models.
Section 1. Inside Mixture of Experts. Let's take a look under the hood.
Okay, let's dive into this terminology so we are all on the exact same page as we move forward. In a Mixture of Experts model, the neural network isn't just one giant monolithic block of math. It's actually broken up into specialized pieces. So you have R, which stands for a routed expert. Think of these like highly trained specialists. Maybe one is fantastic at math, while another's a grammar whiz. They only activate when a very specific token is routed to them. Then you have S, the always active shared expert. This expert fires on every single token, capturing the kind of general baseline knowledge that everyone needs. And finally, we have dense layers. Typically, the very first few layers of a model just use a standard dense feed-forward network before any of the complex routing even begins, just to get the initial processing out of the way.
To really understand why this matters, look at the sheer scale of these models. The Kimi K3 model has a staggering 2.78 trillion total parameters. But, and this is the crazy part, because it uses a mixture of experts, it only actively uses about 104 billion of them at any given time. That means less than 4% of the model is actually firing to generate a response. DeepSeek V4 Pro is super similar, 1.6 trillion total parameters, but only 49 billion are active. By separating the model out into these experts, AI developers can scale the brain up to trillions of parameters without needing the insane processing power required to run all of them simultaneously.
Section 2, the load balancing problem. Having all these incredible specialists brings up a major logistical nightmare.
Imagine you're running a massive workplace. You've got a dispatcher handing out tasks to 100 different specialists. What happens if suddenly 90% of the tasks coming in today are about math, and your dispatcher tries to send every single one of them to your one math expert? Well, the math expert gets completely overloaded, the entire assembly line grinds to a halt, and your other 99 experts are just sitting around drinking coffee. In AI, if the router sends all the tokens to just a few routed experts, the model bottlenecks. Processing literally slows to a crawl, and the system completely loses its efficiency. Load balancing is absolutely crucial here. It's the mechanism that prevents this expert overloading by ensuring tokens are fairly and evenly distributed across the entire specialized network.
Section 3. 3 routing solutions. So how do we force the AI to distribute the workload fairly without ruining its accuracy? Based on the architecture data, modern models generally tackle this traffic jam in one of 3 ways. First, there's the traditional approach, known as G-shard or switch auxiliary loss. Second, we have a newer, leaner method championed by DeepSeek, which is auxiliary loss-free. And third, we have a highly statistical approach used by Kimi K3 called quantile balancing. Let's break these down.
First up, Method A, the classic G-shard approach. In simple terms, this method uses something called an auxiliary loss. It actively monitors the load ratio, basically keeping an eye on how many tokens are going to each expert, and if things start getting unbalanced, it applies a mathematical penalty. Through gradient updates, it basically reaches right into the router and forces it to change its behavior. Now, it definitely works, but it's a bit heavy-handed. It actually requires calculating and applying an entirely separate loss function during training just to keep the traffic moving.
So, the natural question is, what if we could balance the load without that heavy direct penalty? Well, enter DeepSeek style balancing. Instead of an auxiliary loss, it dynamically updates a bias based on load statistics. Think of it like this. Imagine the routed experts are different nightclubs, and the bias is the bouncer adjusting the cover charge at the door. If a club is totally underloaded and needs more people, the bouncer adds a positive bias, basically letting tokens in for free. But if a club is overloaded, they slap on a negative bias, jacking up the cover charge to turn tokens away. And here is the real genius part. This bias only affects the selection process. Once the token is inside the club, the bias doesn't alter the final mixing weights at all. It's just a much lighter, more dynamic way to manage the traffic.
And then we have Method C, Kimi K3's quantile balancing. This one gets incredibly clever.
Kimi K3 also completely ditches the traditional load balancing loss function, but instead of using a simple positive or negative bias, it uses heavy statistics. It looks at the router scores for the top experts it selected, plus one extra, what's called the top K plus 1 cutoff. By looking at the mathematical margin between the experts that made the cut and the one that just barely missed it, it can precisely calculate the bias needed for the next step. It then mean centers that bias across all the experts. So it's essentially predicting the exact mathematical nudge needed to keep the system perfectly balanced on the very next step, based entirely on those score margins. No penalty required.
Section 4. Real-world model comparison. Let's see how all this theory actually gets applied out in the wild.
Now, what's really interesting about this is the sheer variety in how these top models are built. If you look at the configurations, Kimi K3 is just massive. Out of 896 routed experts, it selects 16 per token, plus it uses 2 always active shared experts. DeepSeek V4 Pro takes a noticeably tighter approach. Out of 384 routed experts, it selects just 6, alongside 1 shared expert. And GLM 5.2 is smaller still, selecting 8 out of 256. Every single developer out there is actively trying to find the perfect golden ratio of total specialists versus how many you actually consult for any given token, all to maximize speed and minimize compute.
But some models are literally throwing traditional conventions entirely out the window. Standard MOE models use compute-heavy routed experts, meaning even if an expert is highly specialized, running data through it still costs processing power. But consider Longcat 2.0. Alongside its standard routed experts, it actually integrates 128 zero-compute identity experts. This is sometimes referred to in the space as MOE++. Basically, if the router decides a token doesn't actually need complex processing for a specific layer, it routes it to a zero-compute expert, which essentially just passes the token right on through without doing any heavy math at all. It's a completely brilliant way to save compute on simple tokens while hoarding that big processing power for the really complex ones.
Finally, I have to briefly highlight a few specific architectural quirks, just to show how much wild innovation is happening right now. Kimi K3 uses something called Stable Latent Mo for its first layer, where it actually compresses the input into a latent representation before routing it, saving massive overhead. DeepSeek V4 Pro? It doesn't even use standard routing for its first 3 layers. It uses Hash Mo, where the expert is predetermined purely by a hash function of the token ID itself. No complex routing required. And Qwen 3.5 takes a Class A approach where its shared expert isn't just automatically added in, it actually has its own separate scoring gate. The sheer engineering diversity out there is absolutely staggering.
So, we started today by looking at how AI prevents traffic jams, and we've ended up uncovering the very mechanisms that allow these models to grow into the trillions of parameters. By utilizing mixture of experts, load balancing, and incredibly clever routing math, developers are quite literally breaking the physical limits of hardware compute. Which leaves us with a pretty fascinating thought to take away from this explainer. With models already reaching 2.78 trillion parameters today, purely through the power of intelligent routing, how will these efficiencies dictate the future scale of AI tomorrow? Are we honestly looking at a future where 10 or even 100 trillion parameter models run seamlessly on standard hardware just because the routing is that good? It's wild to think about. Thank you so much for joining me to explore the hidden architecture of the AI revolution.